Welcome back to the wireless channel, everybody. Today we have a very exciting video in which we will go through the implementation on AFDM using USRPs, following the same material that you can find in our previous works published on AFDM. The presentation will be given by our very own Eric Hyun Sok Roo, who you could say left this as a very nice gift for us since he's set to very soon take up his professorship in Korea. So, Eric, thank you very much as usual, and please take it away.
Okay, so thanks for the introduction. Without further ado, we can begin with the presentation, which again is going to talk about the recent AFDM implementation that I did over 2 USRPs that we had in the labs. I believe it's one of the very first AFDM full over-the-air demos available and that we have also shared. And at the end of the presentation, we also have a nice surprise for the community regarding this as well. So as you mentioned, the first objective in this whole project, a mini project for me, was to translate and validate everything that we did theoretically and mathematically in our recent papers and put it to practice, so demonstrate it over the air. And this is one of the things that we were lacking in the literature. And of course, what I wanted to do was not just make it work, but to follow what we have outlined and what we described was the case for AFDM. So as you can see in this little figures, that we claim that AFDM could be very easily implementable by simply adding some new blocks. So here in these light green blocks on top of the dark green OFDM blocks. And so with minimal changes, we can implement the full TX-RX chain of AFDM. So this image is pretty much what I started with as well, which you can also find in these two papers referenced. And I started building this on MATLAB as well. So first, to describe the setup that I used. So we had 2 USRP B210s. So these are kind of the very baseline USRPs with good functionality that we have. And also I used MATLAB and its communication toolbox. So I didn't use Noon Radio. It was fully MATLAB from beginning to end. And the setup that I began with was simply an indoor office environment. So I had the 2 fully unsynchronized USRPs, 2 fully independent PCs. So as you can see here in the image here, we have a USRP, we have a mini PC behind it as well, connected to it, and just a screen. And these 2 setups are identical. And one is the transmission at the TX side, one is the reception at the RX side. And these 2 PCs are fully independent and unsynchronized. So of course, we have to perform the synchronization, the CFO correction, and then the channel estimation, and so on. And here are the parameters that I used for this setup specifically. Of course, this is tunable within the code, but I just wanted to start with the not a very full-blown scenario, but just a carrier frequency of 2.4 gigahertz, a master clock rate of 16 megahertz, and then the filters up conversion and down conversion filters of 16 samples, 16 times. The sample rate of 1 mega samples per second at the USRPs. So from the MATLAB to the USRPs, the USB 3 cables are transmitting at 1 mega samples per second. And of course, there's the transmit and receive gain, which were tunable. It's hidden here, but you'll see later there is a tunable knob that we can tune at the 2 sides. So to go into the transmit block structure that I used, of course, we have some input bits and we have the blocks that convert the bit to symbol. So I used an MCOM constellation with gray mapping. And then we have the resource grid assembly and the pilot insertion. So in the scenario that I used, I had 256 number of subcarriers and we had 24 AFDM symbols. I mean, AFDM symbol in time. And if you see the structure here, this column is 1 AFDM symbol with 256 subcarriers. And what we have is we have some 0 nulls and a single pilot, then another set of nulls. So this is 17 nulls, then a single pilot at the 18th subcarrier, and then another 17 null. And all of the remaining is the data symbols. So this structure is what is from the actual original paper from Benani. AFDM, they propose to have this guarded uh, piloting structure, as we'll also come back to it later in the receiver side when you use the channel estimation. So this is strictly to perform simple integer grid channel estimation. And then after the resource grid assembly, we have, of course, the inverse discrete affine Fourier transform, which is implemented using the formulation in our various papers, and even from the first paper, where we do first an element-wise phase rotation with some given chirp rate, which I have here with my parameter, then a simple IFFT block, then another chirp rotation based on the second chirp rate. So after this IDAFT, we can perform the prepending of the prefix. So of course, normal AFDM requires, general AFDM requires the chirp periodic prefix. But in this setup, these parameterizations, we have that the chirp periodic prefix reduces to the simple cyclic prefix of OFDM. So this is what I use just for simplicity. And then we append the preambles. So here, the preambles that I used for synchronization and CFO correction, the single STF block and two Zadov-Chu sequences. The first one is also a long Zadov-2, 10 Zadov-Chu sequences performed for a coarse synchronization. Then we have two Zadov-Chu sequences that is used for the correlation and then perform the fine tuning of the CFO and the synchronization. And we have the data or 24 symbols of AFDM following that. And then on top of that, we have now the pulse shaper. I use the RRC filter of 5 times. So we go from 200 kilochips from the after the preambles, then to the 1 megasamples per second that we have denoted before between the Matlab and the USRP. This is the parameterization of the filter, roll-off filter. And then we just perform a peak normalization such that the maximum is normalized to 1. And then we have a digital intermediate frequency and a zero pad. So of course we have the zero pad before and after the symbol. This is just to, for the sake of the proof of concept, we have some zeros for some radio silence between each symbol. So it's like a burst communication just between each block. And this digital IF means simply that we just have a shift. I believe I had a 240 kilohertz shift from DC just to prevent some DC spur from the hardware and perform clean signal processing. And then after that, we simply go to the hardware and then we upconvert to the actual wireless signal that we get. And of course, we have the next receiver side. We get the wireless signal at the USRPs. We remove, so we shift it back to the zero frequency. Then we do the coarse synchronization and the fine synchronization. So the coarse synchronization is done using the Schmitz and Cox algorithm, and we simply perform the correlation. We get this nice plateau as we usually know. This is used to perform the coarse synchronization, obtain. And then we use the fine synchronization with the two Zadov-Chu sequences. And this is used to find the actual peak and the actual estimated carrier offset, carrier frequency offset that we can correct for it in the next block. So after this, we are fully synchronized, and then we perform, of course, the match filter and decimation after the pulse. And then we have two steps here. One is for the noise estimation. In my setup, I simply took the lead zeros before the actual signal, as you can see. So this is when the coarse synchronization field started. This is the lead zeros. And based on this, I estimate the noise. And of course, on the side, we have the actual demodulation. So we perform the discrete affine Fourier transform, the forward version. So we have the phase rotation, the forward FFT, and the second phase rotation. Then the last step, of course, is to perform the channel estimation. This is, again, using the very first proposed embedded pilot approach. So we had the guarding, the single pilot, and the guard. Using that, we can estimate the grid, the delayed Doppler grid in the integer grid. So we have Doppler tap of 0, delay tap of 0. We have the integer delay taps. We have the integer Doppler taps. Here, this is just the grid that I used in this estimation that was supposed to supported by the number of zero pads. And you can see that simply in the indoor scenario, we clearly have a single delay and single Doppler tap. And then based on that, once we have the channel, we can go and perform the MMSC equalization based also on the noise estimate we have from here. Then after that, we simply demap the symbols to the bit and we get the output bits. Again, this channel estimation and equalization is nothing novel. It's just a fundamental algorithm proposed in this journal. So that was the description between the transmit and the receiver side. And here we have the actual demo videos. So the first setup is a close-up, a closed scenario where we have just about 1 meter apart. So this is actually just a photo, but in the actual video here, it was further apart. And of course, here we only have a single delayed Doppler tap. Here we have the synchronization correlation here. This is the selected peak. We have the equalized constellation, and we have the track EVM here. So this simply shows that we have a fully unsynchronized 2 USRP running the pulse-shaped AFDM simply. And then we also went ahead and performed this across different scenarios. We had a larger setup in the indoor corridor of our university. This was about 50 meters, I believe. This was also transmitting all these symbols without any problems, fine. We also took one side of this outside and we took it to a field. So here is the other side of the building indoors. Here was about 200 or 300 meters outside that was receiving the symbols over AFDM fully. And that was fine. Transmitting again, the full channel estimation seems to be correct. And we also get the actual image correctly as well. We also did a fun application where we linked it up to a webcam and then transmitted a live video over this AFDM link, which also, again, you can see the full stats here. And it was also performing everything as expected. Then, of course, we have to compare the AFDM against OFDM. And of course, this is not a full analytical comparison. It was a demo-based comparison. And for firstly, we have to match the actual profiles between the two OFDM and AFDM. Note that I used a pulse-shaped OFDM, not OFDM with null subcarriers, just for the sake of simple comparison between the two. So both systems have 256 subcarriers, and it was specifically matched such that both systems have the same number of data, the same ratio of pilot to data ratio. So AFDM requires these nulls plus the pilot. So all of this number of pilots were scattered around the OFDM for this comb-like structure of the pilots. So this orange is the pilots. And here we just have a single null. This was just to match the total number of data points, such that the two have exactly the same number of bits transmitted over the total 24 symbols. Based on that, here is the screen capture video of the two. So of course, note that the synchronization blocks between the two are common. So both OFDM and AFDM systems use the same Zadoff-Chu sequences in the STF and the two fine-tuning synchronization blocks. So those two are identical. And then we have the two spectrums. So one is the OFDM in green, one is the AFDM in orange. So you can see between the spectrums, you can see the equalized symbols, you can see the estimation of OFDM channel. This is the estimation of the AFDM channel as a delayed Doppler grid. Of course, OFDM just uses the simple conventional OFDM channel estimator and equalizer. And you can see that everything pretty much remains identical. Of course, you have the difference in the EVM where AFDM seems to perform better. But here, because the delayed Doppler tap is 0, it's not because of the waveform itself, it's simply because of the actual channel estimation approach that we used and the equalization approach that we used. So if this was to change, this is also changing. So this is not because of the waveform at this point. And then we also did some fun tests comparing the two. Based on this, we did some image transmission between the two devices, fully unsynchronized. You can see that the original image here, and you can transmit one with the OFDM chain, one with the AFDM chain, the same scenario, same setup, same number of bits, and we get the total received live demo of the two. And in the end, we come to the last promise after all of this description. In the beginning, we promised a bonus gift to the community, which is giving the first public AFDM implementation code to the best of my knowledge. This is the first repo online that you can just simply download and experiment with the MATLAB code, which has the full AFDM demo in the USRP running. So this is what you can see if you go to this repository. If you have the TX side GUI, which is pretty much the same thing as we have here, the transmission side. And here we have the receiver side GUI where you can see all the stats and also the two OFDM and AFDM received image, which you can simply replace on your own. And you can also change the gains and the constellation sizes on each side. And you can therefore experiment on your own USRPs, validate it, and also hopefully build on top to see really expand the AFDM literature, not just on the theoretical side, but also now providing many demos and applications as well. So that is it. We close off and thank you very much for attention.
Thank you very much, Eric. Once again, guys, any questions? I have one question, somewhat boring but important
Mm.
nevertheless, which is what would you say are the take-home messages regarding the challenges of doing the implementation and learned lessons in terms of what do you think that might have been overlooked in much of the literature on AFDM when it comes to the actual implementation?
That's actually a very good question because if you just go from the OFDM implementation and try to do just build on top, you actually come across a few challenges. And one thing that I can say is the biggest take home message for me was if you simply follow this literature that we did, all of these blocks are true. So you can simply do these additions, and everything will be fine. But the biggest difference that I didn't realize here was when we perform the actual conversion. Here we have this important block that I put this digital IF. So if you look at the spectrum, maybe I can go to the spectrum image. You can see here at the zero, of course, because of the hardware, there is going to be some DCs per. So in OFDM, you can either put a DC null and just remove this or remove the effects that is going to be detrimental for signal processing. But here you can see what I did was a digital IF. So I've shifted this to a higher frequency for the processing. And this is actually because you cannot simply put a zero null, oh sorry, DC null for AFDM. Because in OFDM, if you just null the DC, you get rid of this. But if you null the DC, I mean, if you try to null the DC in AFDM, this is not possible because every single subcarrier spans the entire bandwidth. So even if you null one of them, it spans the every other subcarrier spans the entire bandwidth. Whereas here, if you null the zero, there is no frequency at the zero, right? So this is the key difference. And I think when you tried various implementation before, this was causing a lot of problem. Of course, if you have this, your IQ imbalance is going to be quite large, such that your synchronization is going to be quite bad, and so on. So the first thing that I found was the synchronization was not so easy just using AFDM. That's why I resorted to that of Chew. And looking into it now, I believe this nulling is also one takeaway message. But other than that, everything else really stays as is, as illustrated in this image. You can see all of these blocks are pretty much identical to OFDM as well, except these phase rotations and the different channel estimator.
Thank you. That's very nice. Anybody else, guys, or questions? Is there any hands up?
There's
Okay,
not.
I see DDA is also there. DDA, can you hear us? Do you have any questions?
No, no, it was a very clear presentation. Thank you, Eric, for the presentation.
Thank you.
Okay, thank you very much. So, any last words then, Eric?
So I guess just the last words would be please feel free to access this GitHub and try it for yourself. All you need to do is just go to this, download the two folders, one at the transmitter side, one at the receiver side, and it's really interesting to see these new waveforms working over the air. And you can build on top and do various stuff, but just don't forget us, right?
Hmm. Okay, then thank you very much, guys. That's it for today, and I see you next time in the Wireless Channel. I bid you goodbye now.